Right now, I'm on a submarine, and it is so cool. There's so many cool fish and coral to see this deep underwater. But now that I think about it, how do engineers design submarines? Or anything involving fluids at all? Fluids have so many interesting properties to think about when designing these sorts of things, it must be hard. And it is, but not everything engineers have to think about is as complicated as it first seems. Hi, I'm Annika, a first-year student studying creative technology and design at CU Boulder, and today let's explore some of the key ideas behind working with fluids. A large part of engineering is fluid mechanics. Just about anything you make involves dealing with fluids. A fluid is any matter that flows, which includes both liquids and gases, meaning almost anything an engineer designs, boats, cars, planes, even buildings, has to take fluid behavior into account. Let's start by diving into a question I know I've asked, and you probably have too. Why do boats float? To answer that question, we need to understand Archimedes' principle. This principle states that any object submerged in a fluid experiences an upward force, called the buoyant force, equal to the weight of the fluid it displaces. In simpler terms, when you put something in water, it pushes some of the water out of the way, and the water pushes back. This principle also comes with a mathematical formula, which states that the buoyant force, the upward force from the water, is equal to the mass of fluid displaced times gravity. The mass of fluid displaced is the density of that fluid times the volume of the fluid that is displaced. And you can simplify the equation to say exactly what the principle itself says. Buoyant force is equal to the weight of fluid displaced, since weight is mass times gravity. Let's look at an example. Say you have a rubber duck displacing 10 milliliters of water. We figure out the mass of that water by multiplying the volume we are given, 10 milliliters, by the density of water, 1 gram per milliliter. Thus, the mass of that water is 10 grams. Then we multiply that by gravity, which is 9.81 meters per second squared. This gives us 981 grams times meters per second squared. Then we convert that into 0.981 kilograms times meters per second squared, and because we don't want to say that whole unit over and over, we simply call it newtons. Thus, the buoyant force acting on the duck is 0.981 newtons. But how exactly does the buoyant force make things float? Well, an object's weight is the force of gravity pulling on its mass. Thus, an object's weight is a force pulling the object downward. The buoyant force is a force pushing it upward. So, if the buoyant force is stronger than its weight, the object will float up. If the weight is greater, it will sink. And if they're even, the object will stay in place. Engineers use Archimedes' principle in ship design. By shaping boats to displace enough water, they ensure the buoyant force can support the boat's weight, allowing it to float. So, to summarize, Archimedes' principle says that an object in a fluid experiences a buoyant force equal to the weight of the displaced fluid, which determines whether they float or sink. So, that's the first big idea of fluid mechanics. Now, let's look at a slightly more pressing matter. See what I did there? Because the next law is about pressure? Okay, moving on. Another widely used law in fluid mechanics is Pascal's law. Pascal's law involves pressure, which is a measure of force over a given area. Have you ever seen a hydraulic press? Well, they essentially look like this. When you press on the small side with a force, the bigger side pushes upward with a stronger force, even if that side is much heavier than the small side. But why is that? Well, Pascal's law states that a pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and the walls of the container. Basically, no matter how you push on a fluid, all parts of the fluid experience that exact amount of pressure, and so do the walls of the container that hold the fluid. But how does that make the force on the bigger side stronger than the smaller side? Let me explain. Pascal's law is represented by the mathematical formula P equals F divided by A, or pressure equals force divided by area. When you push on the small side of the hydraulic press, you're applying a force over a small area, which puts pressure on the fluid. Since the pressure is dispersed throughout all parts of the fluid evenly, the fluid on the big side of the press experiences the same amount of pressure. However, because the area of the big side is larger than the area on the small side, in order for the pressures to remain equal, the force on the big side must also be larger than the force on the small side. For example, let's say we have two connected containers. The first is 1 foot and the second is 10 feet. If we push on the top of the 1 foot container with a force of 1 Newton, then our force is 1 Newton and our area is 1 square foot, which is the area of the liquid we're actually pushing on. This makes the pressure 1 Newton per square foot. This pressure is distributed evenly through the rest of the system, including within the big container. Since the area of the cross-section of the big container is 10 square feet, the force must be 10 newtons in order to keep the pressures equal. Thus, our smaller push on the smaller side created a much stronger push on the big side. This concept is used in hydraulic systems, like car brakes, construction equipment, and even water distribution and sewage networks. So, to summarize, Pascal's law says that pressure applied to a fluid in a closed container is transmitted equally throughout the whole system, which allows us to multiply force using hydraulics. That's 2 out of 3. Now, let's hurry into the next law. That's also a pun because the next law involves velocity, which can be fast, hence hurry. I'll hurry onto the law now. Finally, let's talk about Bernoulli's principle. Bernoulli's principle states that pressure and velocity are inversely related. As a fluid's velocity increases, its pressure decreases, and vice versa. It's represented by this giant equation. This equation might look complicated, but let me break it down for you. Let's pretend we're looking at a pipe with water moving through it. The two sides of this equation represent a different point along the pipe. Let's say point 1 is over here on the left, and point 2 is on the right. The uppercase P's are the pressure, and the little 1 and 2 next to them let you know that it's talking about the pressure at point 1 or 2 specifically. And to be clear, the pressures can be different here because it's not a closed system, so Pascal's law doesn't apply. The letter rho, the one that looks like a lowercase p, represents the density of water, and this is the same each time it appears. The v's represent the velocity of the fluid, and the little 1 or 2 once again let you know whether you're looking at the velocity at point 1 or 2. The g's are gravity, which is again the same in both appearances. And finally, the h's represent the elevation of the fluid, with the 1 or 2 again telling you whether to look at point 1 or 2. But how is this helpful? Say you're looking at 2 points along a pipe that's angled. This pipe has water flowing through it, and we know the density of water and the gravity here on Earth. At point 1, we know the pressure, velocity, and elevation of the water. At point 2, we know the elevation of the water, and we know that its velocity is higher, but we don't know its pressure. Since Bernoulli's principle says that pressure and velocity are inversely related, what does that mean for the pressure at point 2 compared to point 1? It means that the pressure at point 2 is lower than the pressure at point 1, and we can use Bernoulli's equation to figure out exactly what that pressure is. By the way, this pipe is an example of turbulent flow, where the fluid particles flow irregularly, which causes changes in velocity, and usually occurs in large pipes or other high-flow media. The other kind of flow is laminar flow, where the fluid particles move along a smooth, uniform path called a streamline, and this usually occurs in small pipes and other low-flow media. Bernoulli's principle is a primary component when designing things that move through air, like cars, planes, and bridges. To summarize, Bernoulli's principle says that a fluid's pressure and velocity are inversely related, and there's a helpful equation that relates the pressures, velocities, and elevations of a fluid that is moving at 2 points. Wow, we went through a lot. Let's go back through everything to make sure we've got it down, shall we? Today, we looked into 3 key principles of fluid dynamics. Archimedes' principle, which states that an object submerged in a fluid experiences a buoyant force equal to the weight of the fluid it displaces. Pascal's law, which states that a pressure applied to a fluid in a closed container is transmitted equally to every point of the fluid and the walls of the container. And Bernoulli's principle, which states that as a fluid's pressure increases, velocity decreases, and vice versa. Whenever an engineer designs something, there's a lot to think about, and fluid mechanics is one of those things. Fluids, both liquids and gases, play a huge role in all types of engineering, and now you know some of the key principles behind how they behave. I'm going to go back to looking at the fish now. I hope I'll see you again soon, and until then, keep exploring the wide world of engineering. Check out the full lesson on Teach Engineering. Then use what you learned about Archimedes' principle, Pascal's law, and Bernoulli's principle in the associated activities: buoyancy and pressure in fluids, soda bottle Cartesian diver, rock and boat, density, buoyancy, and Archimedes' principle, and a shot under pressure.